All right, section 3.3 is where we were in the last class session, and we had gotten to the point where we were about to start talking about some whole number multiplication properties. Now, some of these are going to look familiar. We've talked about these with addition and subtraction or subtraction already on some of them. So the first one, excuse me, is the closure property. Now, I know you know that word. Now, you may not remember it because it's been like 2 weeks since you've seen it, right? But that word has come up before, this idea of closure. So again, we'll talk about closure the same way. Closure is the idea that all of this set of numbers, in this case it's the whole numbers, okay, 0, 1, 2, 3, 4, 5, and you can keep going, are all floating around in the room. And our operation that we're talking about now is multiplication. So if we were to pluck any two, or even the same two numbers out of the air, of the whole numbers, and we were to multiply them, we would get another whole number, which is also floating around in the air, and we wouldn't have to open the door. Now, that's unique again, right? We talked about how subtraction doesn't do that. And we're going to talk here in a minute, too, because division doesn't do that either. It's definitely possible to take two numbers, pluck them out of the air, divide them, and not get another whole number, right? So this idea of multiplication in this particular context is actually important. So if we take every whole number a and b, then a times b is a unique whole number. All right, so do you guys remember what commutative property was with addition? What was that one? Right. So like 3 plus 5 is the same as? Right, so you can switch the order. It's the same thing for working with multiplication. So if we have whole numbers a and b, then a times b, in fact, I'll put the dot between them to be clear, is equal to b times a. Okay, the order of multiplication doesn't matter, right? Yeah, it definitely doesn't. 3 times 5 is also the same as 5 times 3. That's just why when I was working with my daughter on multiplication facts, as we increased her multiplication tables and got to the 10s and 11s and 12s, there's fewer and fewer cards that she can't do because she's done almost all of them already, right? Because 10 times 5 was already in the 5s tables. She doesn't have to rememorize that. She already learned that. So 5 times 10 and 10 times 5 are the same thing. Just have a few to add. Associative property. What was associative property? Had parentheses, right? What changed when we looked at it? I mean, lots of things could have parentheses. The grouping, like what was located, not where it was located, but what was located inside of the parentheses. So with multiplication, we've got the whole numbers a, b, and c. We can actually take the three numbers a times b times c. We could put the grouping around the a, b, or we could put the grouping around the b, c, and the multiplication would be the same. Right? So if I wanted to multiply 5 times 2 times 6, there might be some reason why I wanted to multiply 5 times 2 first. Why might that be? Why is 5 times 2 nice? Because it's 10, and multiplying by 10 is really nice after that, right? So there are certain numbers that multiply together really nicely, and there's others that may not. And so there might be a reason to do the multiplication sort of out of order, and that's perfectly fine. You'll get the same answer. Identity property. Now, some of you noticed on your homework that when you said that you had the identity property, I took off if you didn't say additive identity. And the reason is because the additive identity and the multiplicative identity are different numbers, right? The additive identity was the number 0, because 0 added to anything is 0. What's the multiplicative identity? It's the number 1. Because the number 1 is multiplied by anything, it does not change the value. So when we have a whole number a, we can talk about taking the number a times 1 or 1 times a, and we still get back the number a. So this is the identity property, and it is the multiplicative. You can either say multiplication or multiplicative identity. Okay? So if you're going to talk about the identity, I want to specify because it really means something different. Commutative means commutative. You change the order. Multiplicative identity and additive identity are different identities. The zero property, this is a new one. The zero property actually says that when you have a number and you multiply it by 0, what do you get? you get 0, and the order doesn't matter. Part of the reason the order doesn't matter, of course, is because it's commutative. But yeah, we multiply by 0, we get 0. It's everybody's favorite question on the multiplication sheet when they do them in the 60 seconds or whatever they do, timed multiplication test, you guys know? Or you can do that one really fast. Okay. And then the last two properties are really the same property. One says over addition, the other one says over subtraction, but they're the same thing. So if you just said distributive property for either of these, that would be fine. This actually tells you how to combine multiplication and addition, or multiplication and subtraction. And so it looks something like this. If you have A times B plus C, that's the same as AB plus AC. And a lot of times you'll see people draw something like this, or maybe they even put arrows on the end to indicate that you can distribute that across those parentheses. And there's nothing special about addition on this particular one. Subtraction works exactly the same way. So A times B minus C is AB minus AC. All good? Okay, so what we're going to do is we're going to do the same thing we did last time when we looked at these properties, is we're going to look at a list now where these properties are at play, and we're going to identify which property is being used in each case. All right, so again, you can't just look and say, hey, look, there's parentheses, it's associative property, because there's parentheses on every single one, aren't there? So be careful. Don't just think associative means I've got parentheses and vice versa. The first one, what is that first property that's being used?
Zero property.
That is the 0 property. How about the second one? That is commutative. Right? It's not associative because the numbers don't change from where they're located. They're either inside, they stay inside, they're outside, they stay outside. What changes is the order of the multiplication inside the parentheses. How about part C? That is associative. The actual numbers that are inside are different. 3 and 4 on the left and 7 and 3 on the right. How about part D? Somebody even said it right. I think it was Brenna. Multiplicative identity, right? You could say identity for multiplication. As long as you get the word multiplication in there, I'm going to be happy. Okay, some kind of a multiplicative number or a word. How about E? It's that one on E. It's distributive. It looks a little different than you're used to seeing it, I think, which is why you guys are looking at it and thinking, is that, I think it is maybe, but what if she's tricking me? I could tell you were thinking of it. This is a distributive property. These are all properties. You don't have to write them down, but I will. All right, so notice the 5 is actually written behind, but it's the same thing, right? I mean, it would be equivalent, the same thing if I wrote this as 5 and then 3 plus 4. It's identical because that would be a commutative property, right? So writing the 5 in front or the 5 in back is the same thing, and then we're just distributing that 5 across that set of parentheses. How about F? It definitely looks odd. But what is it? It is the distributive property. Very good. What you actually see happening on this one is the 1 plus 2 is being distributed to the 3 or to the 4. So you see the 1 plus 2 now being multiplied by 3, and the 1 plus 2 now being multiplied by 4. It looks odd, I know, but it is just an application of the distributive property. Any questions on those? All right. That's it for multiplication in this section. The next thing we're going to talk about is division. So division of whole numbers. For any whole numbers A and B, there's a few conditions. B is not going to be equal to 0. Then if we talk about A divided by B equaling C, so why can B not be 0? Any thoughts? Yeah, if we actually wrote a divided by b sort of in a fractional form, it would look like this, and so the b would be in the denominator, it'd be 0. We're going to talk a little bit more about why this is actually happening, but that's probably what you remember details as most, is this idea of no zeros in denominators. So if a divided by b equals c, if and only if c is the unique whole number such that a is equal to b times c. A is called the dividend, and B is called the divisor, and C is called the quotient. So I want you to take a look at this. This is how people usually start thinking about division, children, those third and those fourth graders. When they see 6 divided by 2, and they want to know what is the answer here, question mark, they say, what times 2 equals 6? That's what they do. They say, what times the number 2 equals 6? And the answer then, of course, is the number 3. That's all that says up there, is if you have a divided by b equals c, then it's equivalent to have the statement that a equals b times c. Now, it's also important to realize that if you use that description, it becomes very obvious why b can't be 0. Let's say that we had b equal to 0, besides the fact that we know the denominator stuff. Let's just throw that denominator piece of information sort of aside, because we may not have encountered that yet, for instance, when we talk about this. If we talk about a, in fact, we'll use even numbers. We'll use my 6. 6 divided by 0 equals something, and our question is, it's a question mark, right? What is it? Well, it would mean that I'd have to be able to rewrite this as 6 equals this question mark times 0. And there's a problem with that. What's the problem? Yeah, that right-hand side, question mark times 0, I don't care what the question mark is, you're going to get a 0 on the right-hand side. You can't get back to 6, can you? So that's another reason, very concrete reason, why this can't work. It can't work to divide by 0 because there's nothing times 0 that gets you back to anything but 0. Okay, so I want to show you some models for division. Do these say division now on your paper? Do they say models for division? Okay, at one point I had a typo in my notes, and I guess I got it fixed. Good. All right, so let me erase this down here. We have the set partition model. There's 2 set models. The set partition model looks something like this. Abby has 24 rocks, and she wants to give them to 6 of her friends. How many rocks will each friend get? So I'm going to draw a picture for this too, just kind of like what your book is showing you on some of the others that you guys have seen. We're going to do a picture of 24 rocks. All right, I think I've got 24 of them now. Do I? I think so. I think there's 24 rocks there. She wants to give them to 6 of her friends. How many rocks will each friend get? So what you're wanting to do is you're wanting to take these rocks and you're wanting to sort of put partitions in. And you want the partitions to have 6 different locations. This is actually one of the ways that I see this used in the classroom situation. This is what you do when you say, I want 6 groups. And so you go around the room and you say, we're going to count off by 6s. You're 1, you're 2, 3, 4, 5, 6, and we run out, so Shelby's 1 again, right? So what you've actually determined is you've determined how many groups you have. And that might be a really good way to determine groups because maybe there's a certain amount of board space. Or maybe there's only 1 teacher or 2 teachers to go around and you don't want to be filtering between 12 groups. That's not going to work very efficiently if you have to talk and say the same thing 12 times, that kind of deal. So we've actually going to have to take this and we're going to have to break it apart into 6 equal groupings. We're doing them equally since we're working with whole number division. But if I put these into 6 whole groups, this is what I end up with. I've partitioned them off. So how many rocks will each friend get? 4 rocks. So what you've done is you've created 6 groups of 4. All right? I'm just going to write that down here because I want you to see how this is different than the next one. Now, I don't mean that that's the answer, but that's just something to be aware of. The answer is 4 rocks. All right, so let me show you the other set model for division. Your book doesn't distinguish between these two, but when we get into Math 2, it's important to recognize that there is sort of a distinction going on. This is the set partition model variation. So the book that I've used before doesn't call this a partition, but this is a variation that your book is going to give you. So this one instead has Abby has 24 rocks. She bags them together in groups of 6. Do you hear the difference? What's the difference on this one?
She's taking 6 rocks. She's not giving a certain amount of to 6 friends.
Right. Instead of having 6 friends that she gives the rocks to, she's giving groups of 6 rocks. So we, instead of looking and partitioning them off so that 6 people get rocks, we put rocks in bags of 6. So on this one, the answer, how many friends have a bag of rocks, is 4 friends. But it's not because I counted what I circled up, right? What I actually counted is I counted how many groups or how many circles of rocks I have. And this is what happens when you do groups in a class where you actually decide, instead of saying let's number off by 6s, you say I really only want 2 people or 3 people or 6 people or whatever per group, because when groups get too large or whatever, somebody ends up not doing their work. They rely on too much on somebody else or something like that. Instead of determining how many groups you have, which is what you do over here you're determining how many groupings you have. Over here, you're determining how many people or items are in the group. In this case, 6. So over here, instead of, well, the first one was we had 6 groups of 4. Over here, we actually ended up with what? 4 groups of 6. They feel a lot alike, but they actually are constructed quite differently. All right, there's also a couple other models here. The missing factor model. So Abby has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? So the question's not asked any differently. It's the way that you show the modeling of the illustration that looks different. So you have 24, and you want to give them so that each friend gets 6. There is a missing factor here. 24 divided by what equals 6? And so the modeling or the visual for what you get is you're going to have 6 times this question mark. And if you were working with a child who'd already done multiplication, which they would have if they're encountering division now, they would know that the answer that goes in this sort of box or this question mark is what number? 4. So you're filling in a missing piece of information. Okay, again, same question. These questions don't differ much between them as far as how they're worded. It's how you write the answer that actually looks different. That's different from the other models that we've seen with the multiplication and subtraction and addition. Abby has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? Well, this kind of an idea is called repeated subtraction. And it works really well because it's very basic. It actually means that you can do this problem without knowing multiplication. That's sort of weird. I mean, usually you do multiplication before division, so you can rely upon the fact that you know the division, know the multiplication to do the division. But some of the kids are a little bit sketchy on that idea. So this is what happens when somebody works with these kinds of deals. So imagine you actually had 24 rocks in your hand. And you don't know exactly how many each rock the kids' friends get, but you've got 6 people sitting in front of you. Well, what you do is you go, you get 1, and you get 1, and you get 1, and you get 1. Everybody gets 1, and then you look at how many you have left. Can you picture doing that? And maybe you do it for a reason. Maybe you let them each pick their own favorite one, and then they all pick again. Children like this, don't they? They do like this because they get some sort of a control of the situation. So what happens in terms of what this looks like in your modeling is that you take the 24 and you subtract off 6, because that's the first round of pickings, right? They each picked their first rock. 24 minus 6 leaves me with 18. And then we do the same thing again, and we say, okay, well, we can give them each one more rock. And we're subtracting 6 because we're giving 6 rocks away every time we go through our group of friends and letting them pick one or giving one to them. And this is 18 minus 6 would be 12. 12 minus 6 is 6, and then 6 minus 6 is 0. Highly inefficient. Agreed? But does it work? Yes. And what we do is we count up how many times we subtracted off 6. And how many times do we do it? 4. They each get 4 rocks. Now, if the numbers are bigger, this looks a little bit different, and I'll show you how it looks as we do another example. But this is the basic idea, is that everybody gets the same number of something. So I don't have to count anything. I don't have to multiply anything because I've counted instead, basically. All right, so what I'd like for you guys to do, in fact, is, let me see. Most everybody's here. So let's just partner up where we're sitting to do this so that we don't have to move around too much. I want you to create a word problem and solve it with each of the 4 models of division. As we said, most of these, except for the one that's the set partition model down here, excuse me, that variation one, they set up exactly the same way. It's the solving part that looks different. So go ahead and group together. Okay. So I'm not going to write on this, but it's recording if you go back to listen. So somebody give me an example that you used. We'll do one at a time. So just give me your example, and I want you, and then we'll talk about it for the partition model, the set partition model. Do you want to start first?
We said Miss Baker has 32 pieces of candy. She wants to give them to 8 students. How many will each student get?
Okay. So she's determining in advance on your problem how many students get things. Is that right?
She wants 8 students to get the candy, so
she's determining how many students get candy.
Yes.
Yes. So when we're looking at the partition model, one way to do that is to determine how many groupings of something are going to happen. So we have 32 pieces of candy, 8 kids get the candy. All right? So that's one way of doing it. So we can draw a picture. Is that what you did? So you drew 32 candies. I'm sure your candies were much more creative than my circles, but that's what I would use as circles. No? You do circles too. Okay, great. So 32 circles, and then we would group them so that there are 8 groups, right? Okay, so how does that differ from the other partition model? There's 2 ways of doing that partition model. What does the other one look like? Somebody give me your example for the second one, the partition model.
We did, Bob has 30 cookies and he wants to put them in 3 bags. How many cookies will it be in each bag?
Okay, so what you've done then is the number of cookies in each bag is still the same set partition model that Carly talked about.
Oh.
Okay, so that's the same partition model. There's another partition model, though, it's instead. So you've determined how many bags you have. What's the other way of doing the partition model?
Can you say, it's like the same thing, I don't know, but Johnny has 32 blocks. He wants to divide them up into 4 baskets.
4 baskets. You're still dividing them into 4 different
So he wants
groups.
to put 8 in each basket.
There you go.
Baskets.
Yeah, so the other way of doing it to flip it around is telling you how many are going to go in each basket. So if we were using your example, Taylor, we could say how many are going to go in each bag. I have 32. You had 30, didn't you?
Yeah.
I have 30 cookies, and if I put them 3 per bag, how many bags do I have?
Okay.
So the question ends up being how many people get the cookies, how many people get to play with those 8 blocks, that kind of stuff instead. It's a small difference, but it actually becomes much more helpful when we do this with rational numbers in math too. So, how about looking at those for missing factor or repeated subtraction? So some group that hasn't talked, what did you use for your example? I know you used the same example all the way through. Bernard, do you guys want to go? What do you guys have?
We said Josh has 32 marbles. He wants to give some to 8 of his friends. How many will each friend get?
Okay, so he has 32 marbles. So if you're doing the missing factor, what did it look like? I'll write this one out because this one actually deserves a little bit different picture. Did you write out what the missing factor?
32 divided by question mark equals 8.
All right. And then did you do something like this next? So we're filling in the missing factor based on our knowledge of multiplication. Good. All right, one last one, repeated subtraction. So one of you guys are going to go. One of my missing, one of my groups that hasn't talked yet. Saber? Okay.
Ours was Leah has 10 gummy bears. She gave them to 5 of her stuffed animals. How many gummy bears does each stuffed animal have?
Okay. So you had how many gummy bears to start with? What was it? 10. So we had 10 to start with. So what would that look like with repeated subtraction?
She would give 1 to each stuffed animal for the first round.
Which would mean we would subtract 5 because you had 5 stuffed animals? Yeah.
Yes.
So we would subtract the 5, the giving everybody 1, and that would leave us with 5. And then we would subtract 5 again. So we keep doing repeated subtraction until we end up with 0. Yeah. All right, so last thing in this section is to talk about the whole number properties for division. So we had all these properties. These are the list of properties for multiplication. And we're going to decide which of the properties hold for division. And we're starting with the one that I already told you fails, right? Closure. So as we work through these, we're going to identify which ones pass and have the property or fail. And a really good way to identify when something fails is to show an example where it just doesn't work. So closure means that I take two numbers, and they're whole numbers because I'm working in the whole numbers in this description, right? I'm doing whole numbers here. And I need to divide them and get something that's not a whole number. So somebody give me an example. There's lots of them. 5 divided by 2. That's not going to work, is it? Because 5 divided by 2 is not a whole number. Now, could I create a whole number set that does work? Sure. Instead of using 5 divided by 2, we could have chosen 6 divided by 2, and it would work. But if it doesn't work all the time, then it's not a property. So does this property work? No. Closure property doesn't work because this is not a whole number. We'll use some symbols just for fun. Right? That's not an element of the whole numbers. Commutative property. Give me anything you'd like. Somebody give me two numbers. 2 and 3. Is 2 divided by 3 equal to 3 divided by 2? No. Commutative does not work. The order of division highly matters, right? Big deal. Associative property, you run into the exact same problem. Let me write down the associative property, the one I have, because I have all the simplification done already for us. Let's say we did 12 divided by 4 divided by 2. And then we'll do it in the other order, 12 divided by 4 divided by 2. Pretty much any numbers you want to use are going to work. This one's just going to keep everything into whole numbers, which is kind of clean. So what is on the left-hand side, we work inside the parentheses. What is 12 divided by 4? 3. On the right-hand side, I work inside my parentheses. What is 4 divided by 2? 2. On the left, 3 divided by 2 is not a whole number. What is 12 divided by 2? 6. So is 3 divided by 2, that is 3 halves equal to 6? No, this does not work. These are not equal. So far, we're 0 for 3. Identity property. And the identity property works in one direction, but it doesn't work in the other. We had the same thing happen with subtraction, right? We could do 5 minus 0, and it still equals 5. We couldn't do 0 minus 5. Same problem with the identity property. We could do 5 divided by 1. You know, that's great, but the problem is that if we do it the other way around, not so great. Right? The division only works by 1 and stays in the same one direction. And of course, that's failing because the commutative property is failing. Do you know what the 0 property was? That was a new property for multiplication. Yeah, multiply by 0 and it was equal to 0. So this one, we'll use the number 7. 7 divided by 0, is it equal to 0? What's 7 divided by 0? Is it? Katrina, what's 7 divided by 0? You can't divide by 0. We already talked about that today, didn't we? Yeah, this doesn't exist. I'm going to put D and E. It does not exist. And we talked about the reason why, right? Is that if I did this, I would have to be able to take 0 and multiply it by something and get back to 7. I can't do that. It's not possible. So the 0 property fails simply because it doesn't even exist. Division by 0 is not even possible. Now the distributive property is interesting because the distributive property works in one direction and not in the other, kind of like the identity property does. So let me show you the direction that it works in. So let's say we had 20, and then remember addition, it's over addition or subtraction, so let's do addition. 20 plus 10 divided by 5. This actually works to divide 20 by 5 and 10 by 5, and it will work with all of the numbers. And there's nothing special about 20s, 10s, and 5s. Now you may not end up with a whole number because it's not closed, but you could actually have this property where you can divide them piecewise and it would work. That's actually a property of fractions. When we get to math 2, you see that. So this is actually okay. The problem is you can't do it the other way. You can't take 5, and even if they were numbers you liked, this would not work. This is not equal to 5 divided by 20 plus 5 divided by 10. No chances. And you can simplify to see that that would not work. But this would actually give me 1/4 plus 1/2, right? 1/4 and 1/2 is much, much larger than 5 divided by 30, right? Same thing up here, though. It does work because this is 20 plus 10. This is 30 divided by 5 is 6. 20 divided by 5 is 4. 10 divided by 5 is 2. That is 6 as well. So it works in one direction and not in the other. So since it doesn't work in both directions, in general, that would be a no. Okay, last problem is a student's work and justifying or thinking about whether her description is correct. Sue claims the following is true by the distributive law. A and B are whole numbers. 3 times AB is equal to 3A times 3B. How would you help her? So the first thing you have to decide is she right or is she wrong? And then secondly, why? So what do you think?
She's wrong.
She's wrong.
You're multiplying 3 twice.
Okay. Okay, so this is incorrect. Okay, so tell me what you're thinking, Taylor.
Well, by distributing it like that, she's multiplying 3 twice. It would have to have addition to be able to be distributed.
Okay, so that's the first kicker, is that we probably wanted to tell Sue, is that the distributive law or distribution is multiplication over addition or subtraction, right? Not over multiplication. It's not multiplication over multiplication, right? Okay, so we can tell her that this is incorrect and that the correct thing is that this would have worked, for instance, if this had said 3 times A plus B, right? And then 3A plus 3B. That would be the correct law. How can we actually show her that what she wants to do really does not work? And she wants to be able to do this distribution. How do we show her that that's really not a property of multiplication the way that she's done it? What could we do? Yeah, let's put some numbers in. When we put numbers in, we put in for A and B, right, Carly? So A and B here are any whole numbers. So if her method works, it should work for any whole numbers. Now, there are whole numbers we could pick that it might work for, so we want to be a little bit careful. But in general, we don't have to be too careful. So somebody pick a value for A for me and a value for B. Don't make them big because I don't want to do big multiplication today. Somebody pick me some small numbers. 2 and 4. All right. So A is 2 and B is 4. So let's actually test her method. So if her method's right, we should be able to do the left-hand side, which is 3 times 2 times 4. And we should be able to do the right side, which is 3 times 2 times 3 times 4. Okay, so we work inside the parentheses. So 2 times 4 is 8, and then 3 times 8 is 24. Thank you. So 24 is on the left-hand side. On the right-hand side, 3 times 2 is 6, and 3 times 4 is 12. Now you get a big multiplication. 6 times 12 is 72, yes. So these are the two answers that we get working with her method. And 72 and 24 are, of course, not the same. So a real concrete, quick numbers, I mean, this is all within multiplication tables because we chose small numbers, right, to show that this doesn't work. What property actually could be used here? This is not a distributive property because this is all multiplication. What property is really going to go on here if you wanted to do something? If you wanted to say there is, in fact, a property that you could use on the left-hand side to change it.
Can you ask that again?
Well, yeah, associative first, right? So, so if you wanted to change the left-hand side, the 3 and then the AB in the parentheses, if you wanted to change that in some way, you could change it using the associative property. See, I could actually say, okay, maybe I don't want to multiply A times B. Maybe that just ends up being a really large number to start with. I don't want to multiply that. But I could instead multiply 3 times A first and then multiply by B. So if there was a reason to do something different, associative property would be what we could use here if there was a need for it. But the distributive property is inappropriate. And it's exactly why, I mean, Taylor said it is exactly why, is you end up with 2 3s. In fact, notice, if you take 24 down here and multiply it by 3, what do you get? 72. It's exactly 1 too many 3s involved because of this distributive misstep that she's made.